everyone, I'm Chaz, Arceneaux. I did the clap-around experiment, and I'm from group 1. So, quick overview of my presentation. We're going to go over the objectives of the experiment, the experiment apparatus and procedures, the governing equations behind the whole experiment, and then we're going to go over the experimental results, which there are questions. Now, I'll wrap it up with a conclusion. So to start off, the whole objective of this experiment is to find the latent heat vaporation of water over the whole range of temperature and pressure. So we want to know how water boils at different pressures related to the temperature that the water actually boils with. And then a unique thing we're going to use during this experiment are the boiling beads. These help create equalization sites, so the water can boil at lower temperatures and it calms the boiling process. So it's not spitting up water where it's nice to get boiled. So we'll start with the experiment apparatus. We have our nice smiley computer right here, which collects all of our data for us. We have the beaker, which holds the water and the boiling beads. Above it is a suction cup, so we can have a vacuum in there. Attached to the suction cup is the pressure gauge and a thermocouple, so we can measure the pressure and the temperature. Coming out of it is where we draw the vacuum from. We have a pump right here that circulates water. Through the circulation, it causes a pressure gradient, which causes the air from in here to move out. So when we start up the pump, we're making it run for a little while until we have a vacuum inside the beaker. Then we're going to shut off the pump and close the valves. And from there, we're boiling the water. And as the water is going to boil at different temperatures, the pressure inside the beaker will raise. And we want to make sure once we reach around 100 degrees Celsius that we open up the air bleed so the top doesn't pop up like it did to us. And then our governing equations is the Kaplan equation, which is the differential or the derivative of saturated pressure over the temperature. And that's related to the heat over the time and a specific volume. An easy way to evaluate this is we use the ideal gas equation to get rid of our specific volume. Instead, we use the pressure again, along with T squared and the universal gas constant. This is an easier way to calculate our results. So here's my experimental results. This is just the data itself. We have right here our pressure and temperature line. So as temperature increased, our pressure also increased. And this is related to the steam tables, which is in our thermal book. So as you see without the beads, we're pretty close to our steam table values. This one's the same experiment with the boiling beads. As you can see, it's a lot closer to where our steam table values are. This is because the boiling helps the beads help the boiling process and with the creation of those equalization sites. Alright, so procedure 1, we use the local derivative to find heat values, the value for the heat constant. And I did this over all our points. All I did was delta P over delta T. And you can see we have a lot of outliers. This is all for without the beads, and with the beads, it's a lot closer. Right here, this line is the expected value for H. And this is a very inaccurate method, just doing the local derivatives. So later on, we're going to get a little bit better. We're going to take the expression relationship of the equation. So what I did is I plotted the temperature, pressure into multiple sections, and I found the slope of those sections to insert it in as a derivative. And without the beads, I did 3 spots. Right here, right here, right here. And that gave us a general slope. And I piecewise them together to make this whole curve. And then for without the beads, I did the same thing, but I used 4. In hindsight, I probably should have done 4 to 5 for without the beads. I just wanted to see the difference between the two. And as you see, we're slightly coming down each time and getting closer to where the curve should be, but with the piecewise function, it's very jumpy. And I believe I had some calculation problems, because right here is where the tabulated H value should be. Alright. And then the third procedure is we found the regression, which is pretty much, we know that the heat is a linear function that goes with time. And then we also solve the Campion's equation by taking the second derivative, and then we solve for the coefficients using the regression. By doing this, I found the constants A and B for without the beads and with the beads. And this is the general curve it gave us. So in conclusion, the boiling beads allows us to boil water calmer and at lower temperatures. Procedure 1 we found is very inaccurate. There's so many outliers that it's hard to get a general curve. Our procedure 2 is a lot more accurate because it's starting to get to where our basic curve should be, but with the piecewise, it's still really jumpy and inaccurate. And then our third procedure is the most accurate we can, because we conclude that heat is a function of linear time, or linear temperature, excuse me. And it has a general linear curve that our H value should have. Is there any questions?